measure of dispersion or spread. So we'll go one by one. With the simplest, first one is range. This is the simplest, most common. As soon as we have a data, we try to find out what is the range. For example, whenever we have a salary, job listing, job posted, right? We try to find what is the range of salary, what is the maximum, minimum. That's the first thing we pay attention to. So that's why range is the most simplest and most frequently used. So that's the first thing what is the spread of the data? What is the minimum, maximum range? That gives me the spread of the complete data, right? How much is the range? Price range, we talk about that. What is the range of price we are talking about? That's the most commonly used, and that's why it's important. It tells me how, in what spectrum is the complete data distributed, the price is distributed, or the salary is distributed. What's the range of that? So this is the simplest measure, simple, and it just range is equal to max minus min. For example, same thing, range of 1, 2, 3, 4, 5. This is 5 minus 1, that is 4. That the range is maximum minus minimum. So this is my range, 5 minus 1, 4. Simplest to do. So this is easy to calculate. That's the pro of this. Okay. And the con is that it is just considering the two extreme values. It is not taking all the data in the distribution into account for measuring this. So only the first and the last, the max and the min, is taken into account. So it is not taking everything into account. That's what is the drawback or the con of this. So it cannot be like the exact representative of this, because it is not talking about all the data points here. That's the con. So the range is simple. Next one is variance. Variance is the actual, this measures the actual spread of data. Spread, how spread out the data is, measure spread of, this is the actual spread of data points. So we have the mean. Say for example, if we have a normal or a Gaussian distribution, and we have the mean here. So this, how far a data point is from the mean, the distance. For example, if this is the mean and my data point is here. So there is some distance. Say my data is x here. So there is some distance between the mean and the data point. So we take this distance and square it, so that that difference is amplified. Okay, the distance is amplified. The spread is amplified, so that we know how spread it is. So we amplified that, and to measure that how actual on both the sides. Okay, so this is, and we square it. So squaring it, what it will do, that I'm just worried about the distance. So if this is like d distance, this is also d distance. So this is like plus t, this is minus t. I don't care whether it is plus t or minus t. I'm squaring the distance. I just want to find out how far the data is from the mean. Okay, I don't care whether you are positive or negative, but you are far away from the mean. So I'll just square it to amplify it, and also to change the sign into positive. So I just discuss about the magnitude. So it solves two problems. First of all, it amplifies the distance. Further, if it is very close, it won't impact much. But as it goes farther and farther, the impact is amplified, and it shows that the data point is very far, and it's easier to measure. For example, if you square it, right, 1, 2, 3, 4, 5, and then 10, like that. So if you see 1 square is 1, but if you see 10 square is 100. Here the difference is only 1 to 10, but here its distance is 10 times that, and this is now 100 times. So due to squaring, the impact of the distance, how far it is from mean, that is amplified. That's what it makes. So the measuring it becomes easy, because it's obvious. Okay, this data is far. I hope you get the point. Okay. So this is measure of distance from. So let me write the formula directly. So sigma square. So that's the symbol. Sigma square is the variance. Sigma square. We'll talk about sigma is standard deviation. We'll talk about that next. Okay. So this is 1 by n, and then I'll be talking about this is the population. Okay. I'm talking about population variance. I'm using this symbol sigma for population, as I discussed here also, right? Whereas, so this is your population mean and the sample mean. Both are different. Population is mean, sample is x bar. Similarly, population is sigma square and the sample would be s square. Okay. And the formula for this will be 1 by n sigma I equal to 1 to n mu minus xi or xi minus mu, whatever, xi minus mu, whatever works. This is for population. Simply for sample, we write it as s square. This is 1 by n. We take it as small n, capital N for that, for differentiation. I equal to 1 and xi minus x bar square. So this is your sample mean. This is your population mean. There is one more square. There is a correction factor called Bessel correction. Bessel correction. So instead of n, we use n minus 1. I'll create another video for that, why it is used. So this is an unbiased estimate. This is a biased estimate, and for removing that bias or taking an unbiased estimate, we instead of n, we have n minus 1. There is some math and calculation, some intuition behind that. That is called Bessel correction. I'll discuss about that sometime. I'll write it Bessel correction for unbiased estimate. Instead of n, we have n minus 1 in the denominator. That makes it unbiased. Okay. I hope this is clear. Simple. So next one is standard deviation. Standard deviation is simple. We have heard about that. Standard deviation. So variance is the spread. Standard deviation is the square root of. Standard deviation is the square root of variance. So it measures the average distance of the points from the mean. Okay. So distance of each point, average distance. So this is square of the distance, and that measures the distance itself. Standard deviation measures the distance, and this measures the square of the distance. That's the difference. So if I have variance, if I take a square root of that, then I'll get a standard deviation. That's what it is. Standard deviation is. So this is represented by sigma, and that simply it is written as same formula, variance of x. This is your sigma. So for example, let's do it. So sigma is like if you see in the Gaussian also, let me draw the Gaussian here again. This is my Gaussian distribution, and for example, this is mu. So the significance of mu in Gaussian distribution, or the sigma, the standard deviation is, so there is one rule called 68, 95, 99 broadly. So 68% of data is one standard deviation away. This is plus minus 1 sigma. This is plus minus 2 sigma. This is plus minus 3 sigma. Approximately this much of data is there. So if the standard deviation is sigma here, sigma. So if I go here, so 68% of my data will be in this range. One standard deviation plus minus. So this is my mu. I go minus sigma here and plus sigma here. This is sigma plus, this is minus sigma. So 34% here, 34% here on both the sides. This is a normal distribution PDF. So 68% of data will lie here. Similarly, if I go 2 standard deviation till here, then 95% of data will lie here. And if I go 3 standard deviation till here, then 99% data will lie here. So that's the importance, and that's what we use on standard deviation. That's the most common utility, standard deviation in Gaussian. And normal distribution, they are very common. It measures the distance of each data point from the, so for example, if this is mu and this is the x point, right? So it measures the distance t from here. How do we do? Let me write the formula. So this is, say for example, I'll give you a standard deviation of 1, 2, 3, 4, 5. This is a sample, right? So what is my x bar? This will be equal to 3. This is my mean. No problem about that. So what will be my standard deviation? This will be equal to square root of distance is always square root of the values. So 3 minus 1 square plus 3 minus 2 square plus 3 minus 3. For each I am taking the distance, what is the difference, and squaring it, and then I'll take square root of all. And then there is 4, then 4 minus 3 or 3 minus 4 square, it doesn't matter, plus 5 minus 3 squaring, and then average distance of all the data points will give me standard deviation divided by 5. This will be equal to 3 minus 1 is 1 plus 4 plus 0 plus 1 plus 4 by 5. 4, 5, 10. So square root of 10 by 5, that is square root of 2. That is 1.4 approximately. Approximately 1.414. This is my standard deviation of this data. Our standard deviation is clear. We have discussed about this a lot. There's one more measure of distribution, data distribution, which is simpler than this. So the units of variance, if you see, that is square, distance square. So whatever is the unit here in variance, that will be square of the distance, square times. Okay, and this is the square root, so the units will become same. Units will become same, whatever the distance. For example, if I'm measuring height in centimeters, so my standard deviation will be in centimeter, but my variance will be in centimeter square. Okay. Another one, next one is mean average, mean absolute. So I want to calculate the distance, right? Mean absolute deviation. Mean absolute deviation. So simple, this is average absolute deviation. Instead of square, it is absolute value. So square will anyway make it positive. Absolute value also makes anything positive, right? Absolute value of x is x. If it is positive x, then it will make it x. If it is negative, also then it will give me x only. It just captures the magnitude, not the sign. Okay, so this is average absolute deviation or distance deviation from mean. Okay, this is less sensitive to extreme outliers. So this is less sensitive to extreme outliers. Say for example, instead of 5, if I have 100 here, right, this 100 will be squared, and this will make the standard deviation move towards the outlier. But if I am not squaring it, the impact is not so much amplified when I use absolute value. So that's the pro of this with respect to standard deviation, mean absolute deviation, that it is less or more robust to outliers. More robust to outliers than standard deviation, because standard deviation uses squared values, which amplifies the difference. Okay, what is the formula for, and in short we write it MAD, mean absolute MAD. This is equal to 1 by n sigma I equal to 1 to 1, same thing, and xi minus x bar. This is the sample mean, and this is the absolute value. So this is average 1 by n, and this is the sum of all absolute value differences. Say for example, same thing if I calculate MAD for that. For example, MAD of 1, 2, 3, 4, 5. This will be equal to, so mean is 3, So this will be mod of 3 minus 1 plus mod of 3 minus 2 plus mod of 3 minus 3 plus mod of 3 minus 4 plus mod of 3 minus 5 by average 5. So this is not squaring. So 3 minus 1 is 2 plus 1 plus 0 plus 1 plus 2 by 5. So this is equal to 6 by 5. That is 1.2. So this is less than standard deviation. So another way, when we have outliers, when you think that there are outliers and its impact should not be amplified, then we consider mean absolute deviation. I hope that's clear. So next one, this is important, skewness. I have discussed this earlier also when I was discussing moments. I'll put the link of that video, but I'll discuss it again in detail here, skewness. So this is the third moment. So when we talk about moments, right, moments of a distribution, this is the third moment, third normal moment. Variance is the second moment, and then we'll discuss about kurtosis, which is the fourth moment. Okay. So this is the measure of asymmetry of data distribution. This is measure of asymmetry of data distribution. For example, if it is a normal distribution, it is bell shaped and the data is symmetric. Half of the data is here, half of the data is here. So around the mean, means half of there, half other side. Okay. And the variance, what variance or standard deviation captured, that whether the data is close to mean or spread out, it is far from mean. That's what the distance measures. But here, if the data is asymmetric or not, none of the metrics measure that. And if I want to measure what if my data is asymmetric towards any of the directions, then skewness measures that. For example, if my data is right skewed or left skewed, okay, it can be like same thing. I have like this, I have like this. So my data can be like this, okay, or it can be like this. You see, this is like right skewed and this is like left skewed. If it is right skewed, it is called positive skew, and if it is left skewed, it is called negative skew. So most of the things here, if you my go-to place is Wikipedia. So let me show you Wikipedia, just a minute. So skewness. So if you see, I'll take the diagrams from here and then I'll show you. It's very good. Refer Wikipedia, I mentioned earlier also. Here it shows, right, negative skew, positive skew. Right, there's one more good diagram here at the bottom somewhere I saw. Where is it? This one. This is a very good diagram. Let me take a screenshot of this and explain you. So I put it in the notes. Okay, and let's come back to the notes. So if you see at this skewness tells me the asymmetricity, how asymmetric my data is. This is the positive skew, which is this is skewed towards right side. This is the positive skew, and this is the left side skewed or negative skew. Okay, and this is symmetrical. This is kind of normal distribution. It is not skewed, no skew in this data. And if you see, due to skewness, what happens is the median, okay, mode and mean. Here, if you see the relative position, so I'll write it here. Just write it, then you will observe what am I saying. So mode is less than, okay, it's on the left side, and median, then the mean. And here if you see, the mean is less than, the median is less than the mode. Why? See, the mode, as I mentioned earlier, mode is of the peak. That's the most frequent element, and therein the PDF will be the tallest. That's the most frequent. Around this number I have seen the most number of times, and so the probability of that number is the highest, and that's where we have the peak. So if you see, the peak is on the positive side skewed, the peak is on the left. So my mode is on the left, that's the least value. And here if you see, mode is, if it is negative skewed, the peak will be on the right side and there will be a long tail towards the left. So here if you see, that mode will become the highest, and similarly mean and median. Okay, yeah, mean and median. And since the data is like tail has become long here, it will pull the mean towards itself. Because a lot of data, the tail is long, so the data, it will pull the mean, instead of the peak, it will pull it towards here, this side, other side, wherever the tail is long. So the mean will be pulled towards the tail, so the mean will go that side. Similarly, since the data is skewed this side, the mean will be pulled this side. And median is the central data, it will always remain in the middle. It's not impacted by, because it doesn't take all the data points into consideration. So the median stays as it is. But this mean and mode will shift. I hope that is clear, depending upon the skewness. That's why understanding skewness or the third moment is important. Okay, let me write it down, whatever I mentioned now. So you saw positive skew. So what is on the positive skew? This side you see, the tail is longer. The tail is longer on the right. Okay, and bulk of the data is here. This is the bulk, but the tail is longer on the right, and just the opposite on this side. That's what I mentioned. And the zero is perfectly skewed. Okay, for example, if you see salary of employees in a company, right? So mostly, if you see, most of the employees earn less salary, but some higher executives, VP, CTO, CEO, CFO, they will earn a lot of salary. So they will pull the mean towards the higher side. But that's not the actual case. Most of the people are earning a modest salary, that they are here. But just few people who are earning on the tail side, like this side, there will be few people here on the tail. This will not touch there. There are few people who will be earning a lot of money. If this is the mean, right, this will be somewhere mean median, right? This is like say an average. So this is like 20 lakh is the CTC average. So some people will be earning in like 2 crores, 5 crores, like that. And this will pull the mean towards right. But that's not the actual representative, because these outliers, this skewness has pulled the mean higher. So in all these cases, if you see, when companies report their median salary, or in the placements also, that median salary is reported, because mean may not be a good representative because of this reason, because the data may be skewed towards one side. I hope that is clear. Why skewness measure is clear, and if I have a measure of skewness, then I will know a lot of information from the data itself. Nobody can then lie to me by saying that average package is this average. Don't tell me the average. Some people might have got very high package. Tell me the median or the mode if there are bulk companies hiring in bulk. So most people will have the same salary. I hope you get the point. Next one, kurtosis, very important. Kurtosis. The names may seem a bit odd, but the concept, if you understand, this is the fourth moment. First moment is mean, second is variance, third is skewness, and fourth is kurtosis. Kurtosis, it measures the tailedness. This is measuring asymmetric, whether data is symmetric or this is symmetric. This is asymmetric, on which side it is asymmetric. This fourth moment measures the tailedness, how fat or thin the tail is. Okay, measures the tailedness of data distribution. How much, so it describes how much data is there in the tail versus the rest of the peak. Okay, it's there. Okay, so, and if I have a long tail, what do I mean? As I mentioned, I have talked about it. If I have a long, fat, thick tail here, right, this means that this is the mean here, somewhere here, mean here, and I have a long, fat, thick tail. So this means that lot of data is there on the extreme side. Means I have lot of outliers. So this kurtosis will tell me that the magnitude of outliers present in my data. Whether I have, if it is a thick tail, then outliers are very much. If it's a thin tail, then the outliers are not so much. That is extreme values. If the tail is thin, means values far from the mean. Those are extreme, right? Values close to the mean are close to the mean. That's the center tendency. So if everything is near, no problem. But if they are far from the mean, then those are outliers. They don't happen. That are not normal. They are rare, exceptional. These are outliers. These are extreme values. And this kurtosis measures that. What is the measure of that outlierness or exceptional values are there or not? So just looking at the kurtosis of the data, we can make out whether we have outliers, and if yes, then what is the how much value they are bringing in there. So let's understand it from the Wikipedia itself. So kurtosis. So I wanted just read through this. This is a lot of information, but I look at it for the graph. So I'll show you this graph. Let's copy it. Then just have a look at this graph. So these are the distributions for many types. As I mentioned, right, there are a lot of distributions. You can't even remember. So we just talked about few which are common, but there are many types of distributions. Just for this data, right? If you see, so here, just read it here. So there are some values here you saw. I just look at here: U, W, N, L, S, D. These names are there, right? Just look at it. What do they mean? D is for Laplace distribution here. S is for hyperbolic secant distribution. L is for logistic distribution. N is normal. C is raised cosine distribution. This is Wigner semicircle, and U is uniform distribution. So there are so many distributions whose kurtosis is drawn here together. And let's come back to the sheet and see. So if you see here, some for this N, right? N is normal, which is color black. So this is the black one. This is a normal distribution. Normal peak, normal tail. This is the normal. Everything is measured against normal. So this is my reference. This black one is my normal. 0. This kurtosis for this is taken as 0. And this is a reference for all. So all these kurtosis is measured with respect to normal. So this is 0, and everything like Laplace is the green one. So if you see, Laplace is green. S is 2. S was secant something. Okay, that is the orange one. And then 3. D was Laplace. S was secant. D was what was T? D was Laplace. L was logistic. L is logistic. D was Laplace. You see, Laplace is so peaked. Okay, and also you see the tails here. So just go through this, and this is very good representation how peaked, if the data is peaked or there. And if you see there's uniform distribution also. There's no tail at all. Everything is in the center. Everything in the center. So no tail, no outliers. Everything. This is a square box. Everything is in the purple box. So this is so U is uniform. That has that negative kurtosis. Okay, no tailedness, 0. Okay, but everything is measured with respect to normal. So let's come back and understand. So it measures the tailedness of data. Okay, and then there was a more thing. So let's see. There are 3 kinds of kurtosis. There's one more diagram probably I saw here. Not here, maybe somewhere else. Let's come back. I'll show you. So there are 3 types of kurtosis. Okay, I'll just take it from other place. I'll just bring the data. Okay, so there are 3, right? So before going through this, let me tell you what am I telling. So you saw there are so many types of, so depending upon these all are having different kurtoses, and these all kurtoses are categorized into 3 broad categories, and normal is the base. Normal is 0 kurtosis, right? and that's what we measure as excess kurtosis. Excess, okay, extra. So excess kurtosis means kurtosis greater than normal. So my normal is considered as my reference, and normal distribution, and this is normal distribution or Gaussian distribution has normal distribution has kurtosis of 3. Kurtosis equal to 3, and excess is anything above 3. Anything above 3. So this is taken as, this has excess kurtosis of, what will be the excess kurtosis of normal? Excess kurtosis of normal or Gaussian will be 0, because this is the reference. So this has basic kurtosis of 3. Anything more than 3 is counted as excess kurtosis. So excess kurtosis for normal distribution is 0, and that's what is shown in this graph, that this is 0. This is what 0 means. Everything, because normal is what is we take as reference, and everything we measure against that. That is the most studied distribution. So excess kurtosis for normal is 0, and everything is measured against that. So mesokurtic is excess kurtosis 0. So this is your normal. This is called mesokurtic. This is your normal. Okay. This is normal, and this is your excess kurtosis is. So normal, and I'll write excess kurtosis equal to 0. That is EK. That is for normal, excess kurtosis is 0. So this will be your mesokurtic. The names are a bit odd, but just understand the concept that this is a normal distribution, and for a normal, excess kurtosis is 0, but its own kurtosis is 3, and that is taken as reference. That's why I make 3 as 0 now. Okay, and kurtosis formula generally, that's a fourth moment, so it has expectation of 4th degree. Okay, so you take expectation of the xi minus mu to the power 4, the expected value of this. This will be a kurtosis. You can see that in the Wikipedia also, somewhere it will be, yeah, kurtosis of x is x minus mu by sigma to the power 4, like that. Okay, so that is to the power 4. That's the fourth moment. So this is your mesokurtic normal. So tails are neither too thin or not thick. That is my reference. So these are neither too thin or not thick. That is my normal. Okay, so not too thin, not too thick. Leptokurtic is the next. This is high kurtosis. The lepto is high kurtosis. High kurtosis means excess kurtosis is greater than 0. EK is greater than 0. Okay, and here if you see, the tails are, this is your normal. If you see here, this tail is fatter. Here, so if you see, the tail is fatter than the normal one for the blue line. This is your leptokurtic. So kurtosis is high, so the tail is thicker, and even the peak is higher than the normal. So more of the okay, high concentration of data around the mean, and also on the tails. So lot of data around the mean, and lot of data around the tails also, lot of outliers also, thick tails. So that is leptokurtic, high kurtosis. Okay. So high, for example, these are like Laplace distribution. If you see Laplace, right? See this Laplace, this thing, D was Laplace. So it has a very peak. So the peak is very high. So a lot of data is around mean, and the tail is also thick. If you see the red one, the tail is also here. The thick tail is here. The tail is thick. That's what we mean. So that is lepto, high kurtosis. And similarly, the opposite would be, for platykurtic would be excess kurtosis is high, kurtosis is low kurtosis, and here excess kurtosis is less than 0, negative. For example, if you see that this is nothing, even the peak is small, and in the tails are also thinner than normal distribution. Okay, so almost like kind of, if you see here, uniform distribution, it has negative kurtosis. So most of the data is uniformly distributed, nothing around the mean. It is not concentrated here. It was like in this Laplace, if you see, it is concentrated on the peak, or it is in the tails. Here everything is uniform. Most of everything is uniform. Nothing around the tails. Everything is uniform there. So kurtosis is negative. No peakness, no tailedness. Here it is very high peak and very high tails. That's what kurtosis will tell you, how my data is distributed. So this will tell me the spread of the data. I hope Kurtosis is clear. It tells me the degree of mostly the tailedness, and if the tail is varying, then the peak will also vary along with it. Okay. So this is your measure of spread of the data, so that I understand what's the measure.